So good morning. Today's lesson is a recap of 2's complement. So it's recapping how we represent negative numbers using binary. In the previous topic, we talked about how to convert between binary to denary and denary to binary. The important thing was that denary, the D-E-N, is like a decathlon. It's to do with 10, as in you have 10 digits on your fingers. So therefore, most human societies count in tens. We have these 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we want to represent a larger number than 9, then we need 2 symbols. But computers, we could have made denary computers, and before binary computers were analog computers, but binary works really nicely because we've just got a really simple world where it's only zeros and ones. And we can do that with light on and light off, or electricity on or electricity off. The idea is we could have had like electricity completely off, a little bit on, a little bit more on, a little bit more on, and 10 different values and have a denary computer. Problem with that is that this is a noisy world, as in if you have an electrical signal like this and there's atmospheric interference that adds a little bit of noise on it on top, I don't know, the moon just got in front of like a satellite, or the sun just burped, or a big solar flare or something, it's really hard to tell apart the noise from the signal. If you just have a really simple on or off signal, it doesn't really matter if you add noise to it, because it's still really easy to tell what the signal is and what the noise is. Why is that important? It means that binary digital electronics can be incredibly reliable. So today we need to be able to understand and use 2's complement. So can you remember what the difference is between sine and magnitude and 2's complement, other than me saying that 2's complement is better? So as a recap, in 2's complement, the most significant bit is worth minus 128 if it's an 8-bit number, and you only have to deal with 8-bit numbers for your GCSE. But if it's a 4-bit number, it would just be minus 16. Or if it's a 16-bit number, it would be minus a big number, like 16 million or something like that. Can't remember what it is. So let's get started straight away with P7. You'll find it in half term 2, binary hex and denary. To begin with, you just need to represent the smallest value. So underneath is the binary, so you can only have zeros and ones in here. This is not the right answer. And above, you need to say what each of these bits are worth. And remember, this is 2's complement, please. So it's 1 and then 2 and then 4. And remember, the most significant bit is a negative number. So just a reminder, on my screen is not the right answer. Just to show you that the top row is how much each bit is worth. You start on the right and you double each time. But the one over here is a negative value, minus 128. And this box in the right is the denary value, the amount that you'd get if you converted this binary number into denary. So the smallest value you'd get if you just have the most significant bit as a 1 and all of the rest as a 0, because then we get minus 128, not add 64, not add 32, and not add any of the others to get minus 128. The largest value, well, we don't want that minus 128, but we do want to add up all of the others. And if we add up all of the others, remember there's only one combination of these bit values for any denary value. There's only one way of representing each number in binary. So for the largest value, the most significant bit is set to a 0 and all of the rest are set to a 1. That helps you with activity 2 because we're now thinking about a different number of bits. Now remember, for your GCSE, you're not allowed a calculator, so you only have to deal with 8 bits or fewer. So even though there is a question here that works in 12 bits, so the minimum pattern is going to be 1 and then 11 zeros, you're allowed to use a calculator for this worksheet, but you wouldn't have to do that in an exam. We only have to deal with 8 bits. So if you want to work this out, we need to have the total unique number of bit patterns is going to be 2, because it's base 2, it's binary, raised to the power the number of bits. And if you want to do this in Word, it's Control, Shift, and equals to raise something to a power. So n is the number of bits. So in this case, n is 12. So 2 raised to the power 12. So 2 raised to the power 12 means 2 times 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 2. A big number. So the minimum value is going to be negative 4096. And the maximum value is going to be one less than 4096, 4095. This is quite easy to work out, really. As long as you know it's 2 to the power number of bits. So you can use a calculator on your computer, you can type it into Google, or you can just work it out yourself, really. So we're going to go through one of the activities for activity 3. This is about binary addition. The key thing here is not to rush. If you get a question on binary addition in an exam, take your time. Make sure you line up your bits carefully, as in leave enough space between each one, and that they are in columns, and then it's dead easy to do. It's exactly the same as column addition at primary school. You start on the right, and we just add together. So 0 add 1, 1. 0 add 0 is 0. This is nice and easy so far. 0 add 1 is 1. Now 1 add 1 is 2, but I can't write 2 in binary with just one digit. So I have to put the 1, 0 like that, because 2 in binary is 1, 0. So it's 0 carrying the 1 onto the next bit. Next, I've got 0 adds 1, but I've also got a carry bit over here. So I'm actually adding 0 add 1, which is 2. Remember, 2 in binary is 1, 0. And then I've got 1 add 1 is 2. 0 carry the 1. 1 add 1 is 2. 0 carry 1. 1 add 1 is 2. So I've got an overflow bit here. I've only got 8 bits to play with, but I've got an overflow bit over here. Now we want to check our answer. So let's see. Can I do this in a different color and see if it works? So let's put the bit values on top. Okay, so this one is 8. This one is, well, if it was all ones, it would be -1. And then we add 2. So it's going to be a negative number. So we added them all together, we get -3. If you do 8 add -3, well, 8 add -3 is just 8 take away 3, which is 5. So hopefully 4 plus 1 equals 5. It just works. So that's the beauty of 2's complement. If you do addition, it works, and then you can also do subtraction, because you can just add a negative number to do your subtraction. So work your way through, take your time, make sure you write down your working out. If this was an exam paper question, you'd get 1 mark for the right answer, and you'd have to show you're working out. Remember, you are not allowed a calculator in your exam. So you should show you're working out. You can use paper for it if you want, but preferably just keep a note of it in your Word document underneath. Just want to remind you of the quick methods of converting 2's complement. So I've told you to write them out, to write out the bit value above each one, as in that's 1, that's 2, that's 4, that's 8, that's 16, that's 32, that's 64, and that's -128. That works, and you should always do that. But remember, there is a quick way too, because it's called 2's complement, because you invert it and then you add 1. So what does that mean? If we know that this is a negative number, and it is because it's a 1 here, then we can say that is the negative value of all of the bits inverted, that means swapped around. So this time it's going to be 4 zeros, another 2 zeros, and 2 1s. And then add 1 to that and make it negative. So that is 3. Add 1 to that makes it 4. Make it negative is -4. Another way of thinking about it, well, this is almost all of the 1s. All of the 1s in 2's complement is going to be -1, because we'd have -128 plus 127, all of those numbers added together, except that we haven't got all the 1s, we've got these ones here. So it's like -1 take away 2, take away an extra 1. So minus 1, take 2 is minus 3. Take away another 1 is minus 4. And that's what we've got here. So there's always a quick way here, as well as that long, safe way of writing it out by hand. I put an extension on here too, in case you finish in good time. Have a go at writing a program that generates 2 random 8-bit numbers like these and gets the user to type them in. And if you get far enough, try and get Python to do the conversion for you and check and see if you get it right. It's pretty challenging, not expecting you to finish it, but do have a go and make sure you copy and paste your code in before you upload it. It's not the end of the lesson at the moment, but at the end of the lesson, please make sure this is saved and uploaded onto Half Term 2 binary, denary, and hex.